In this video of the Soil, Slopes, and Streams series, we'll talk about weathering within soils and rock. We'll focus on the processes by which rocks weather to help soils form on hill slopes. This includes the physical processes that break up rock, move material down slope, the chemical processes that dissolve and alter minerals, and some of the biological processes that do both. Physical and chemical processes act to create and change regolith, like we see here. This is the unconsolidated material at Earth's surface, including soils that provide that substrate for life. These processes together convert the rock at depth to the soil and dirt at the surface. Physical weathering disrupts rock, often prying it apart, providing pathways for water and life to alter it further. Chemical processes occur by chemical reactions that alter minerals, dissolve some minerals, and relieve their constituents to waters, which may flow out and away to rivers and eventually lakes and oceans. Weathering processes can set the stage for how landscapes, such as this one, evolve. We'll start with physical weathering processes that break up rock and regolith. Examples include freeze-thaw processes that heave apart rock, salt expansion, thermal cracking, root growth, and exfoliation. Each of these physically breaks down rocks into smaller parts. Freeze-thaw is a process whereby repeated pressures due to ice growth can crack rock. The process is also known as frost weathering or frost cracking. Here we see an example of frost cracking on a boulder in Iceland. Every period of freezing and thawing means ice expands and contracts with melt, regularly putting pressure on the rock, creating fractures for more ice to grow. You can see this pressure and expansion of ice at work anytime you accidentally freeze a bottle. Here we see a broken bottle due to the effect of ice pressure when the water inside freezes. This is a good corollary to the processes that occur in rock with frost wedging. Salt expansion is a similar process. Here, as water infiltrates small cracks in the rock, salts can form, and the physical precipitation of salt helps to put expansional pressures on that rock. Another example of a physical weathering process is thermal cracking. You may have seen fire-fractured rock, perhaps following a wildfire or even in a fire ring at a campground. But there are also smaller scales and smaller amounts of thermal expansion that occur in rock. For example, on warm days, this rock in the Sierra Nevada thermally expands. This thermal expansion has been linked to rock falls in Yosemite and other areas as the rock thermally expands and contracts on cool days and expands during warm days and contracts on cool days, occurring over a period of weeks and months and years and decades. Physical weathering also includes pressures due to vegetation growth, especially trees. Just looking at this photo, it can be difficult to determine which came first, the crack or the root. It's a chicken and egg problem. However, we know from our own sidewalks and streets that tree growth can be quite effective at physical weathering. And then, lastly, exfoliation acts as a process by which rocks like granite expand along surface joints, especially on curved domes, as we see here in the Sierra Nevada. This is the half-dome granodiorite, which is roughly 90 million years old. Granite rocks like we see here form deep in the earth, and exfoliation is thought to occur as the overburdened material is eroded away and the rocks are exhumed. Exfoliation occurs because the tension is perpendicular to the surface. Pause this video here to follow the link to watch a granite dome pop under pressure and exfoliation in action. The spontaneous rock exfoliation that was visible in the video you just watched occurred during a hot summer day in 2014. It's estimated that 8,000 kilograms, or over 17,000 pounds of rock popped into the air that day. The fact that it was a warm day is probably not a coincidence, as we already learned that the thermal processes can help crack rock. As you can imagine, the conversion of coherent bedrock to these onion skin-like bedrock sheets that we see here provides all kinds of new surfaces to undergo additional erosion processes, physical weathering processes, potentially contribute to rock fall, and give us surfaces for chemical weathering reactions to act. We'll now look at the chemical weathering processes that alter and dissolve rock and regolith. These processes convert coherent material to weathered material, and they act along the fractures and spaces that are physically weathered. To understand chemical weathering, we first have to start with a chunk of rock. Rocks are made up of minerals. For example, in the granodiorite rock at the lower right, strongly related to granite and often termed a granitic rock, we can see these minerals in the different colors of the specimen. Let's zoom in further under a microscope and view these minerals. When we view the minerals under microscopes, we often change the way light moves and reflects, resulting in an appearance with slightly different colors as we see here. This helps the minerals, their nature and boundaries, to really pop to geologists and mineralogists who view them. Though there isn't a scale for this image on the left, it's likely a few millimeters to a centimeter in diameter. The main minerals we see here are plagioclase, hornblende, quartz, and diorite, and biotite. They're distinct and they look different because of their structure and chemistry. They have distinct combinations and amounts of different elements, such as silicon, iron, magnesium, calcium, potassium, and others. And if some of those elements sound like vitamins that you might take, keep that in mind for later when we talk about how weathering has biological links as well. Each mineral forms at different temperatures and depths in the earth. This is known as Bowen's reaction series. Picture this box as a body of magma, and as it cools, minerals form from the melt. Some minerals crystallize at the highest temperatures. These are the upper ones within this box, like olivine and pyroxene and northite. This has pretty important implications for how weatherable minerals are, because minerals that crystallize first in the really hot magma are unstable at Earth's cool surface. And minerals that crystallize last, or when the magma is relatively cool, are the most stable at surface temperatures. This means that the minerals at the bottom of this box, that are the last to form from the melt, are also the last to chemically weather away. You might notice here that quartz is one of the last minerals to form and therefore also one of the last minerals to weather. This makes sense to you, likely, and you've seen this in action in probably a lot of different landscapes. For example, if you pick up a handful of sand at the beach in a setting such as we see here, or within sand dunes such as we see here, or if you pick up a handful of sand in the Colorado River, you might see mineral grains like this. We see a host of different minerals here, but mostly quartz because they're left in this residual physical material as other minerals have been weathered away. Let's go back to this view of the minerals under the microscope. In the unweathered or largely unweathered rock, we should see original minerals like this. Let's now start to physically weather this rock, open up cracks, mechanically break it up. The physical processes then help chemical processes to begin to dissolve and alter minerals. Water and microbes and plants and things like CO2, which forms carbonic acid when combined with water, become really important for these chemical weathering reactions to start to attack minerals. Some minerals will preferentially dissolve away, while others, like quartz, stay behind. But if we look at a sample that's been weathered, we will see this alteration, like we see here in the image from a scanning electron microscope. Look at this mineral quartz. It's stable and stalwart, while others like plagioclase begin to dissolve in water. And as this happens, some elements are lost to the fluids, they flow through the pores and out to rivers, but some elements stay behind, and these can be left to form clay minerals. Check out the space near the bottom of the image. In the scanning electron microscope image, it appears to be black with polka dots. It's a root. The plagioclase mineral can have a lot of sodium or calcium. It's what plants crave, and the root sucks up these nutrients. This is called biological weathering. As the physical and chemical processes we've learned about occur, they act on almost every scale, from the nano and micro scales to the millimeter and centimeter scales to the rock and landscape scales. They interact with one another, often in a positive feedback whereby chemical processes encourage physical processes and physical processes encourage chemical processes. These feedbacks help to shape landscapes, form soils, give substrate to life, and release nutrients to ecosystems.